Is the following statement true, that for all integers a, b, and c, if a divides b and a divides c, then a divides the sum of b and c? Well, let's think of some examples. So let's take 2 for our a. So we can say 2, we know 2 divides 4 because 4 can be written as a multiple of 2, right? That's what for a to divide b means. It's basically saying b is equal to what's a times some integer. Now it must be, again, that, like I said, this has to be an integer. Same thing for something like 3 divides 6. It means 6 can be written as 3 times some integer, right? Or, my bad, shouldn't have said k here. There we go. So yeah, in other words, this is saying what's on the right can be written as a multiple of what's on the left, or what's on the right is equal to what's on the left times an integer. So I'm gonna stick with 2 for now. We'll do 6 for our 3 for our second example. So for 2, we know that 2 divides 4 and 2 divides 6 because 6 can be written as 2 times an integer, where in these cases k has to be equal to 2 and m has to be equal to 3, right? 2 and 3 are both integers, which means this statement is true, which means that statement is true. Okay, fantastic. Now let's ask ourselves, well, does 2 divide 4 plus 6? Or can 2 divide 10? Well, when we're asking this, we have to ask, can 10 be written as 2 times something? And the answer is, of course. This is the same as saying 2 times 5. So now that we got something on the right that's on the left as a product, or in a product, we can say that this statement is true. A quicker way of having done this is you can look at this and factor a 2 out. So you could say 2 divides 2 plus 3, and then this is of course an integer because it's equal to 5. But the important part is we got what's on the left, we got that on the right hand side as well, multiplied by some integer. Fantastic. Now let's give 3 a shot. Let's take 3 divides 9 and 3 divides 15. Now we know that this is true because 9 can be written as 3 times an integer. What is that integer that 3 has to be multiplied by? It's of course 3. And 3 divides 15 because 3 can be written as, or 15 can be written as a multiple of 3, in which case 3 has to be multiplied by 5. So we know that these two are correct. So now let's ask ourselves, is it true that 3 divides 9 plus 15, or does 3 in fact divide, or let's take our second method here, let's factor out a 3 here. Is that possible? Yes, it is. We can say this is the same as asking, does 3 divide 3 times 3 plus 5? And of course, this is an integer. This is what's on the left. So this is true. Or for completeness, let's just rephrase this as asking, can 3 divide into 24? So can 24 be written as 3 times x? And the answer is yes. X here would have to be equal to 8, which is in fact an integer. So it's looking like it's true for our 2 cases here. And I can't really think of a case where this wouldn't be true. So let's go ahead and try and prove this. So before we prove this, we of course need to know the exact definition of divisibility, which is going to be that for some integers a and b, where a divides b and a cannot be 0. Why are we adding this statement? I haven't mentioned what's on the left not being able to be 0. Well, that's because if you think about it logically, because a divides b is basically saying what's on the right-hand side can be written as what's on the left multiplied by some integer. If this was equal to 0, that means to find the integer, you would have to ask yourself, b divided by 0 is equal to k, and you can't do this obviously because you can't divide something by 0. That would be undefined. So take, for example, 0 divides, let's take 2. Well, can 2 be written as a 0 times something, 0 times k, for example? The answer is no, because if you want to find what your k is, you'd have to ask, okay, well, 2 divided by 0 is equal to k, but you can't say that because 2 can't be divided by 0. Or, yeah, well, I think that should be more than enough to explain why we have to add that statement in when we're defining divisibility. So we have to then also say then b is equal to a times k for some integer k. There we go. We have a working definition of divisibility. It is when two integers are such that one integer divides the other, where the integer that divides the other cannot be equal to 0. Then the integer on the right can be written as a multiple of the integer on the left for some integer k. Fantastic. Okay, so now let's start writing the proof. This is a for all proof. How do we start for all proofs? Well, we start with the word let, and what do we let? We let a, b, and c be integers such that, and now we suppose our p statement, such that a divides b and a divides c, and a cannot be 0. Fantastic. We can then say, then b can be written as a times m, and c can be written as a times n for some integers m and n. There we go. We've defined and supposed everything we needed to, so now we need to look at what's on the right-hand side here for our Q statement and ask ourselves, can b plus c be written as a times something in big brackets where this in brackets must be an integer? So let's give that a shot. We start by saying, next, b plus c is equal to am plus an. And of course, you should see here you can factor out an a. So you can say this is the same as saying a times m plus n. Well, there we go. We've now written it as a, what's on the left-hand side here, multiplied by some bracket. And all we have to do is say, hey, m and n are both integers, which means the sum of them also has to be an integer. So we have to say where m plus n is an integer. So now we can conclude our statement is in fact true. So we say, in conclusion, a divides b plus c because b plus c can be written as a times m plus n. So b plus c is a multiple of a. Fantastic. We've now proven that this statement is in fact true.